is here. Oh, not quite. Another minute. Right, well, so it falls to me to chair this session, because if I said I should. So it's a pleasure to welcome Markus Müller, who is going to tell us about that long title there. It is from Göttingen.
Okay, thanks for the introduction. So let me start out with the people who did the work. So the first part was with Kostas Daulis, who was a postdoc in my group, and where we sort of developed a mapping between particle-based models and the Ginzburg-Landau type of functional. And then together with Julia Smirnova, Giovanni Marelli, and Mark Fuhrmans, as well as Anchang Shi from Canada, we used this method then to look at transition states in membranes. The idea is to go between a particle-based model, where you describe the configurations by the positions and the interactions between particles, to a continuum description. And this occurs in several places. And I added here one slide on the problem where you have sort of a particle-based fluid which condenses into a droplet, and then you want to describe the properties of these droplets, because we worked on this with Uwe Thiele, where you can ask, of course, if you want to make this mapping between a particle-based model and a continuum description. I mean, first of all, what kind of continuum description you would like to have. In this case, for the droplet, you could describe just the configuration by the position of the interface and its interactions. So in order to macroscopically describe the droplet, you would need the volume of the droplet and, of course, the surface tension. And then through the balance of the surface tension at the three-phase contact lines, you would get the contact angle of the droplet, which is, of course, well known. If you want to do it a little bit more detailed, then you want to describe the interaction between this liquid-vapor interface with the solid substrate, which gives you the interface potential or the destroying pressure. And we derived a nice method to calculate this without applying to grand canonical simulations, which would be the typical way to calculate that. This balance of stresses, or of tensions, I should say, which dictate the static contact angle, also refers, you can transfer this to a balance of stresses at that interface between the solid and the liquid, and this gives you, of course, the Navier slip condition, where you balance the viscous stress inside of the fluid versus the friction stress as the fluid slips past the surface. And we also looked at these questions, how to extract the slip length here, which is this, the ratio between the shear viscosity of the liquid and this friction coefficient, and the position of the interface, both at simple and at corrugated surfaces. You can ask yourself, for example, if I have such a corrugated surface, where should I apply the hydrodynamic boundary condition? Is it at the top of those pillars or at the bottom? And actually, it turns out that it's quite a bit inside of the fluid. But that's what I don't want to talk about today. These are sort of liquids with a free surface. I'd like to talk about multi-component systems, which don't have a free surface, but the interfaces are given by the interfaces between the two components A and B. And more specifically, I'd like to talk either about blends or about, in the second part, diblock copolymers. These are these molecules which consists of two parts, the red and the blue part, which are joined together and hate each other, so they cannot macroscopically phase separate, but form these mesophases, which are periodically ordered phases. The length scale is set by the size of the molecule, and it's conveniently in the range of 10 to 100 nanometers, and therefore it has attracted quite some interest for templating patterns. The nice thing from a computational point of view is that those different phases, you can see here, the simplest one is just this lamellar phase where you form sheet-like structures, are fairly universal in the sense that you can find them in synthetic block copolymers, where you have basically van der Waals interactions as typical interactions. You can find them in amphiphilic polymers like PEO polybutadiene, where you have an aqueous solution, and you find them, of course, in lipid systems as well, where they form membranes or surfactant systems. That universality suggests that you can use very simple models to describe the structure formation in these systems. What you need is the repulsion between red and blue and the fact that they're joined together in a single molecule, because otherwise the system would macroscopically phase separate. So we will use this very, very simple particle-based model, which only incorporate those irrelevant degrees of interactions, i.e. the connectivity along the backbone of the molecule and the repulsion between the two blocks. And still, these particle-based simulations are demanding, and therefore we want to go one step further and describe them in a continuum description. And so in this hierarchy of models, you could of course start out with an atomistic description. You end up with this coarse-grained model, which I just described, where one bead sort of represents a collection of atoms which interact then via these simplified interactions. And then you could go to continuum description, where you describe the configuration of the system just by the local densities. That is something what DFT people would like to do. And then, of course, you can even take the limit and let the widths of those sheets go to 0, and you end up with Helfrich type of interactions. Today, I just want to talk from this step here, from a coarse-grained particle-based model to this continuum description. So here the degrees of freedom are the particles with simplified interactions, and here the degrees of freedom are continuum fields of the density of A and B. Okay, so let me start out with a particle-based model just to write down some formulas, like was said yesterday. It's a very simple bead spring model. So you have bonded and non-bonded interactions. The bonded interactions are just harmonic springs, so Ri of S is the position of bead number S on molecule number I. Neighboring ones are joined by a harmonic spring, and that basically parameterizes the Gaussian chain configurations. Then you have two types of non-bonded interactions. They are given in terms of local densities. One, the one here, is a repulsion between A and B. The strength of the repulsion is parameterized by this combination of chi times n, the Flory-Huggins parameter. And so if the system becomes purer in A, so this one becomes 1, this one is 0 with a minus sign, it reduces the energy, and that drives the phase separation. Of course, these are dense systems, so the total density does not fluctuate. It's nearly incompressible, the system. So the sum of the density of A and the density of B should add up to a reference value. And so the energy or free energy increases quadratically. And the coefficient here in front is the inverse isothermal compressibility. You can construct now different models depending on how you relate those local densities to the particle coordinates. There are sort of two ways. Either, formally you would define the local particle density as a sum over delta function at each position where there is an A particle. So you can either sort of smear this out by a Gaussian. That would give you a DPD type of model, or weighted density functional theory if you want. Or you can throw a grid over your system and collocate those particle densities on the grid. And that's what we do, actually, because it's much faster for dense systems. Okay, so that's the particle-based description. And of course, I should mention you can generalize this to more complicated non-bonded interaction-free energies, which gives you the advantage that you could look at, for example, bilayer membranes, which have a gel transition here. You can introduce packing effects and so on. It's a quite general formalism where you sort of cast the non-bonded interactions in terms of this density function. Okay. So these are the particle simulations. So you have the degrees of freedoms are the coordinates of the particles. You have these intra and intermolecular interactions. These are the beads and springs, and these is this weighted density functional. The dynamics of the system is you locally move those beads, which gives rise to Rouse dynamics, typically, and they are characterized by a local friction coefficient, zeta. On the other hand, you want to map this onto a continuum theory, where you have the local densities of A and B, and since the system is nearly incompressible, you can actually get away with just one order parameter, which is traditionally the difference between the A density and the B density. So if you think of what type of free energy functional would describe your system, then it would be sort of the classical Ginzburg-Landau-de Gennes free energy functional for a binary mixture or a blend of polymers, or Ota-Kawasaki or Swift-Hohenberg functional if you look at diblock copolymers, which forms then to these mesophases with a given periodicity. If you would like to study the structure evolution, then you could use time-dependent Ginzburg-Landau theory with a conserved order parameter, something like model B according to Hohenberg and Halpering. And so the friction, which sort of characterizes the dynamics in the particle-based model, goes over into the Onsager coefficient. Since these are polymers, the Onsager coefficient could also be non-local, just because if you pull somewhere here with a chemical potential on your polymer, then the force is transmitted along the backbone. That gives rise to a non-locality in this.
Very shortly a question.
Sure.
You said model B is for conserved order parameters.
Right.
And that's because phi A minus phi D, if you integrate it over the whole volume, is conserved.
Yes, it's also locally conserved, right? So because in this dynamics here, you sort of move a bead from A to B, from one, no, not from A to B, from one position to the next position. So you have a continuity equation, right? And so in principle, it's also clear how to go from here to there, right? So the first step where you go from particle coordinates to densities is also used when you basically construct the model. So you put a delta function at each place where there is a particle, and this gives you the density here. It's also clear how to construct this free energy functional. I mean, formally, you would have to take the trace over all particle configurations which are compatible with this distribution of the order parameter, i.e. where the microscopic difference of A and B densities equals to the order parameter you describe. So one thing is you want to calculate this in order to get this free energy functional here. And there's another formula which also relates the friction to the Onsager coefficient. This has been worked out a long time ago by Kawasaki and Sekimoto, and is also consistent with the formalism of Hans Christian Oettinger, where the Onsager coefficient is just the average over the transformation from the particle coordinates to the densities. That's this term here. And this one here is the inverse friction matrix, which ideally for the Rouse model is just 1 over the friction coefficient and then diagonal.
So you use the Rice model basically, so you ignore hydrodynamic interactions in the sum.
Yes, I mean, this is a dense system and there are no hydrodynamic interactions, right? And because we study the particle-based model with smart Monte Carlo moves, where you sort of use the force to, propose a move, there's no momenta and something like that. That is a good description. And if we look at the dynamics in our simulation, it nicely compares to the Rouse dynamic modulo some fine features due to correlation Hall effects.
A question.
Sure.
Why you have this sum over S is placed around of time there?
The sum over S? No. I is the number of polymers and S is the coordinate which runs along a polymer.
Oh,
so
okay.
there are n beads on a molecule and S runs along that.
Okay.
Did you say it's a concentrated system?
Yeah, it's a dense melt.
Wouldn't you worry about entanglement? Sort of thing?
That's a good point, another talk. The thing is, since we have these soft interactions, right? I haven't stressed this, but the interactions are soft, like in a DPD model. And the bonds are harmonic, so they can be infinitely extended. In principle, it costs free energy, but there's no hard limit. It's not like in a Lennard-Jones model with Fehner potential, where the combination of excluded volume and finite extension of a bond guarantees that they cannot cross through each other. Here they happily go through each other. If you would like to include that, you could try to do this via slip links. And Alexander Lichtmann had worked on this, and we also have worked on this. So for the moment, no hydrodynamics, just purely Rouse, you should think of. Okay. So then, of course, you may wonder, well, why do you want to do this in the first place? I mean, you have this nice particle-based model. It's supposed to be pretty fast, so there are two problems with these particle-based simulations, and both of them you can sort of mitigate by this. One thing is the barrier problem. So suppose during your time evolution, there's a free energy barrier you want to overcome, so your particle-based simulation may just get stuck in this metastable state, and you have to wait forever until you overcome this barrier. If you knew where the barrier is, or if you could draw a figure like that, then the problem is already gone, because there exist thousands of very good methods to overcome free energy barriers. The problem is you have to recognize where they are, and you have to find a good reaction coordinate which drives you over the barrier. So one question is, can those methods, this mapping, help you to find a reaction coordinate to overcome these barriers? And the second thing which I would like to start actually are intrinsically slow processes where there's no barrier. The structure formation just goes downhill in free energy. Very nice. It's just very slow. And it can be slow for two reasons. One reason is that your equations are stiff, i.e. that you have a very high frequency component, which are typically the bonds, and you have a very weak force, which are the non-bonded forces. And if you integrate your equations of motions for the particle-based model, then you have to adjust your time step to the high frequency modes. The typical way to deal this would be RESPA, reversible multiple time step integrators. You could also do single chain mean field simulations where you've replaced the weak non-bonded forces by an external field temporarily. But what I want to talk about is this heterogeneous multiscale method where you sort of extract the free energy functional and use this information to accelerate the process. The second thing where why things may be very slow if they go downhill is that the Onsager coefficient is very small. So yes, there is a thermodynamic driving force, but it just doesn't translate into a current. And the typical situation for this case is that you want to move one component across a domain of another component. The Onsager coefficient here is typically proportional to the density of that species, so it's proportional to phi A. In an incompressible system, actually, it's proportional to phi A times phi B, because the fluxes of A and B have to cancel. And so if you have to move something through an almost pure domain, the Onsager coefficient is very small. Okay, good. Let me give you two examples of those intrinsically slow processes. The first example is the following. So suppose, you self-assemble two lamellar sheets, and for some reason one lamellar sheet is thicker than the other one. Actually, the other one is so thin that it ruptures and forms a pore here. And of course, in thermal equilibrium, what will happen is that at the end, the two membranes will have the same thickness. And so what happens very slowly is that, okay, there are chains evaporating, condensing here, and vice versa, and eventually they figure out which one has the lower chemical potential, and thereby the thickness will equilibrate. And this is shown here, which shows the density difference of those two layers versus time. And yes, it just decreases. Even if the pore closes, which was sort of a surprise, which is this time here, nothing happens. There's no barrier associated with this. It just goes slowly through. And it takes a very long time. So the time which is measured here is in the diffusion time of the molecule. So they diffuse something like 90 times their end-to-end distance, or half of the lamellar thickness. Okay. So this is one thing. You can also turn it around and make the water blue hydrophobic and the red hydrophilic, and then you have a stalk which just disappears. It's just symmetric to it. Good. This is one where you have this time evolution which is very, very slow. The other one, which is very classical, and therefore I will discuss this in the following, is where you have just a droplet of one component in a matrix of the other, and you have a big droplet or a slab in the surrounding, which is called Lifshitz-Slursoff growth coarsening, and the physics of that is quite intuitive. So here the chemical potential is different because you have a Laplace pressure. The pressure is higher. The chains inside of that domain evaporate and condensate onto those slabs. And the time evolution, here is just the model B again. So the time derivative of the order parameter is given by the divergence of a flux, and the flux is the Onsager coefficient times the gradient of the chemical potential. If you just do dimensional analysis, you see that the size of that domain cubed goes linearly in t, so in this time with a negative sign because the domain shrinks, which means that as you watch the thing in time, the volume of the droplet linearly decreases in time because the chains, there's a net flux from this curved domain onto this flat domain here. Why is it slow? Well, it's slow because of two things. I mean, first of all, if you look at the Onsager coefficient, as I said, it's proportional to phi a times phi b. And inside of this pure red domain, the concentration of the blue phase is just very low. The other thing is you can also look at the interactions in our model. So if you have the bonded interactions, the typical interaction is kBt over the bond length. And if you rewrite this into the polymer units, then it's square root n divided by the end-to-end distance. So it goes like square root n. The non-bonded interaction is kBt over the monomeric interactions over the width of the interface. If you put in the correct polymer units, then this is proportional to 1 over n. So the power of n to the power of 3/2 difference between the bonded and the non-bonded forces, the bonded ones being the stiff ones. Okay, so that's the problem, and that we want to speed up by mapping the system onto the Ginzburg-Landau model. So the first task then is to estimate the free energy, the Ginzburg-Landau free energy of the model. Then the second task is to use the Ginzburg-Landau model to propagate the configuration of the system, which is described by the density fields. And then the third part is to drag the particle-based configuration to the new configuration of the Ginzburg-Landau model. And then you can recycle the whole thing. Okay, so these two, where you estimate the Ginzburg-Landau simulations, needs a particle simulation, and this one as well, when you want to sort of recreate a new particle configuration which corresponds to the time-propagated Ginzburg-Landau model. Okay, so how do you calculate the Ginzburg-Landau model? Something which we call field theoretic umbrella sampling, because it just looks like umbrella sampling on a continuum. You add to the Hamiltonian, which you already know, these are the bonded and non-bonded interaction, this additional Hamiltonian. And this one says, whenever the microscopic density, which is characterized by this hat, deviates from the density given by the order parameter, the free energy increases quadratically. And the strength of that quadratic or harmonic potential is given by lambda n. And the assumption is lambda n is much stronger than all other interactions in your system. So you basically restrain composition, fluctuations of the microscopic composition away from the value of the order parameter. And you do this for A and for B. Okay. So how does this help you? Well, if you simulate this restrained system, then the partition function will have the Boltzmann factor of this Hamiltonian, so e to the minus beta times this. E to the minus beta times this is a Gaussian. If you let lambda n go to infinity, i.e. being larger than all other interactions, the Gaussian converges to a delta function, and these just generates you the delta functions you need for the partial trace. Okay? Then you can say, well, I still can't do the partition function of that restrained Hamiltonian, but I can calculate the chemical potential, i.e. the derivative with respect to the order parameter here, and you get the chemical potential is the derivative of the free energy with respect to the order parameter, and that is the derivative of the restrained system's free energy with respect to the order parameter, and that I can just calculate by normal standard thermodynamic integration as the derivative of the Hamiltonian with respect to the order parameter thermally averaged in the restrained ensemble. Okay. What it really boils down to, since this is just so simple quadratic, what you have to measure is the difference between the order parameter you impose and the microscopic order parameter you measure, and multiply that by the strength of the umbrella potential. Okay, that gives you the chemical potential, and therefore you know something about the free energy. Okay. You can also do this via the forces, but I think I skipped this part. In principle, you could calculate local forces and then say the gradient of the excess chemical potential is equal to the local force acting on A particles. In both cases, you get the chemical potential for a given order parameter as a function of space, and now you have sort of two options. Either you do what is called equation-free modeling by Kivrakidis and Hummer, where you say, okay, that's all what I need. I have the chemical potential as a function of space, so I just plug it into my model B calculation, and I make my next time step for the continuum model. That will work, but it has the advantage that whenever an interface moves, right, the chemical potential will change significantly, and you have to reparameterize your chemical potential. Okay. The other thing, and this runs under this heterogeneous multiscale modeling, is you make an ansatz for the continuum description. So you say, okay, I have an idea how the functional form of that continuum free energy functional looks like. And in this simple case, we have a very good intuition how it should look like. It's the Ginzburg-Landau-de Gennes functional, so it has a bulk part and then a square gradient part. And I say the bulk part is the ideal part and an excess part. And I just fix sort of the coefficient in front of the square gradient and one or two coefficients of this excess part here. Which says I have 2 or 3 parameters, and I have the whole density of the whole system, I mean all the grid points, to fit these 3 parameters, which I can do very easily, which helps me to do this mapping in a short time. That's one thing. And the other thing is, once I have the functional form of the free energy, I can use it for a much longer time, because this functional form is not supposed to change if an interface just moves. It is supposed to change if the character of the interface changes. Like if I go from weak to strong segregation, or if diblock copolymers would absorb on these interfaces. But if just the interface moves and nothing else changes, I can reuse this free energy functional. So that's very nice. And this allows us to use this free energy functional basically once parameterized for the entire process. Okay, so how does it look like? So what is plotted here is the volume of that droplet versus time, and the time becomes even larger and larger. What is shown in these 3 different colors are just direct simulations of the process for different incompatibilities, a weak, an intermediate, and a strong incompatibility. And what you see is that the higher the incompatibility, the longer it takes. There are sort of 2 things. I mean, the surface tension, of course, increases if the incompatibility becomes higher, so the driving force increases, but the Onsager coefficient decreases much faster. So the driving forces increases like square root of the incompatibility, but the Onsager coefficient goes down exponentially in the incompatibility, i.e. the more incompatible the system is, the slower the process is. Okay. Then we fitted the Ginzburg-Landau model to the system, and we used sort of the literature value for the Onsager coefficient, which is taken from a Rouse chain in a disordered melt. And then we get this black curve here, which has a very similar shape, but gets the time scale slightly wrong, which is not surprising because sort of the chains are oriented at the interfaces and so on. And so if we sort of fix the time scale just by the slope here at the initial time and reduce it by 25%, the Onsager coefficient, then when we fit it here, we can describe the whole process with one Ginzburg-Landau free energy functional and with one Onsager coefficient. Okay, so that's good. So then what we want to do is we want to stop somewhere here, propagate only the Ginzburg-Landau model, which is the squared line, stop somewhere here, and then get a particle-based configuration at that point. Okay, so the propagation of the Ginzburg-Landau model is easy. I will not say anything about that. Yes?
Do you have a feeling for why the Onsager parameter was different? by that amount? Is it
I don't have a feeling why it is different by that amount. I have a feeling why is it different.
Yeah.
Because, I mean, the assumption of the calculation is that it's a perturbation theory around a homogeneous state. While here you have a strong interface, i.e. the chains will distort and align. And it's just at that interface where the mobility, where the Onsager coefficient is important. So the correlation between orientation and deformation and chains and their dynamics is the answer.
I suppose what I'm asking is, do you have a way of being able to predict that rather than fitting after the fact?
There are, we fitted it from the time evolution here. That's one thing. The other thing which we haven't tried is this Kawasaki-Sekimoto formula. That would account for the chain configurations, but it needs the pair correlation function of the oriented chains at an interface, which I don't have. One can measure this, but
Thank you.
okay, so you propagate the Ginzburg-Landau model. I would be curious if somebody has some experience of propagating it with fluctuations. Without fluctuations, it's very easy. With fluctuations, maybe it's just my numerics, which is stupid, but I run into some trouble. But anyway, that would be interesting to learn over the coffee break. But let me focus on, now you propagated the Ginzburg-Landau model, the droplet has shrunken, and you want to get a particle-based configuration for that shrunken droplet. Actually, it's very easy to do this. You just do the same. You just use this umbrella potential and plug in the new order parameter. Okay? If you do so, then if you look at the sort of free energy functional for the restraint system, then it's the free energy functional of the original system plus this umbrella term. If you take the chemical potential of that, then it's the chemical potential of the original system times this, which is a linear driving force to the new configuration of the Ginzburg-Landau model, the strength of that being lambda n. So crank up lambda m and you have a huge driving force which drives the system to the new configuration. And the speed up is just proportional to this lambda n, which in principle would tell you, well, crank it up to the highest value you can think of. And if you have a shallow variation, so this graph shows how you can relax the sinusoidal density fluctuations with this method here. And it scales in the way you would expect it to scale. Since it's a diffusive process, the relaxation time of a mode is proportional to q squared, and the rate is proportional to lambda n. So the higher lambda n, the faster the relaxation rate. That's good. You would also see some non-local effects of the Onsager coefficient in these curves here. There's, however, one catch, and the catch is, of course, at some point it has to break, and it breaks at this point where the strength of the non-bonded forces, now of the restrained non-bonded forces, becomes comparable to the strength of the bonded forces. Then you're certainly dead, because then you have to adjust your time step to the strong non-bonded forces. That's one thing. But this gives you still a whole range, because the ratio between the non-bonded and the bonded forces was this factor n to the power of 3/2. So n being the degree of polymerization, you have a certain range here. And you can choose the non-bonded forces, the restrained forces, to be comparable but slightly smaller than the bonded forces. That's nice. The other thing is, this argument with the chemical potential, of course, relied on linear response theory. The bad news is linear response theory breaks down at lambda n equal 1. Okay? Which means if you have these strong restrained forces, your chain configurations may not be in equilibrium at the end with the density fields you imposed. Which means you may have another molecular relaxation time, the whole chain configuration relaxation time, in order to get your chain configurations correct.
So
Good.
do you have why is it lambda n is equal to 1, that the linear response breaks down? Is there a simple argument? Because
yes.
Your restraint forces are just some quadratic potential differential which tries to bring the particles to respect the density fields.
Right.
So why is it?
Because suppose you want to drag the chain through the melt, right? And you want to do this in linear response, and the drag force can be extremely small only before you leave the linear response regime, and it's exactly the same calculation here.
So it's really the chain degrees of freedom.
Yes.
Chain degrees of freedom that is not linear response.
Yeah. I mean, for bonds or so, you're all fine. But it's the whole. I mean, since you apply a force to the chain, you can deform the chain, and since the relaxation time of the chain is so long, you leave the linear response very early. Okay, but it's not so bad because I mean the total. Even if you give this extra molecular relaxation time, it's not so bad because the total time scale you can bridge is about 80 or 40 relaxation times. So that gives you the speed up. So just to summarize this, you start with a particle-based configuration, you create this Ginzburg-Landau configuration, you parameterize the free energy, you propagate this without noise, as you can see, because all the fluctuations are gone, and you get a very smooth interface, and then you use this order parameter configuration and that particle-based configuration to create a new particle-based configuration. This relaxation from here to here, I mean, the snapshot is at 0.1 relaxation time, so you can make it really fast. And then you give another tau just to be sure. While this one here, if you would do the direct simulation, will take you 81. So the speed up is about a factor of 80 in this case. And then, of course, the test is you have the new particle-based configuration and you just start and let it run, and it nicely continues. So this is after 40 and this is after 80. And that's not so trivial. I mean, you could have said, well, all fine, the droplet has shrunken. Now you initialize the configuration with a shrunken droplet. Should work. But I mean, in order to get the subsequent kinetics, of course, you need that the concentration field decays like 1/r away from the droplet. So that feature you would have to get as well right. And that it continues nicely without a hitch seems to indicate that. Okay, so this was sort of the first application. Yeah.
Maybe it was buried in there, but there must be a small parameter that controls how well you get your new particle-based configuration, because it's not unique, right?
Yes.
And so if you're very far from equilibrium, you might not expect to get a realistic one. So how can you quantify?
Well, of course, one statement is there are many microscopic configurations which correspond to one density field, fine. But I think once you give them one molecular relaxation time, you're good. Right? I mean, yes, I mean, if you drag the chains from all over the place into the slab, right, and the chain configurations may be distorted, but the density is okay. And then you give another one relaxation time, so I think the chain configurations have healed and are typical then for that density profile.
So those mechanic processes are much slower than the actual materialization time.
Yes. Yeah.
So you got that.
Yeah. Exactly. Yeah, that's important. You need this intrinsically slow process has to be much slower than the molecular relaxation time. We tried this first for spinodal decomposition, which was much easier, and it didn't.
Yeah, I was going to ask exactly about that. The stuff that Tanaka showed, viscoelastic phase separation, where you get sort of these sort of bounce-like effect during phase separation. Mm-hmm. You get sort of an inverse pattern.
Yes.
Can you get that kind of thing?
Not yet, but this is one of the open questions in the last slide. I mean, it is very interesting, but yeah. Okay, the second thing is we wanted to use this for the second problem, which is the free energy barrier. And the question we looked at there is sort of stalk formation, which is a biological process which is involved in fusion, where you have sort of vesicles, they fuse with the cell membrane, and then they release their cargo in the outer space of the cell. And the picture about that is you have two membranes, they come close to each other, and then they form this hydrophobic bridge between the two membranes, which is called the stalk. And people believe that the formation of that stalk is important and the determining step for fusion, where you sort of form this and then this expands, forms a hemifusion diaphragm or not, and opens then the fusion pore. As an introduction, you see these stalks in very many different systems, so therefore it's also a good model to look at. So these are stalks in biological lipids. If you have a stack of membrane, you stress them, then you can form these hydrophobic passages, and they condense nicely on an hexagonal lattice. This is a purely synthetic block copolymer, where you find the same thing. So here you see these lamellas and these breakthroughs, which are the stalks, the light spots. And these light spots also arrange laterally on an hexagonal lattice. So that tells you that it's quite universal. And you can look at this as a function of the tension of the membranes and the architecture. Let me skip this. Okay. So this is then one of those processes where you want to go from here, which would be a state with two opposed membranes. And this state here would be where you have this hydrophobic connection between the two membranes. And in between is a barrier, and you don't know how the barrier looks like, and you also don't know what you want to write down on the x-axis of this diagram here. Okay. So the first statement is, and I think it's crucial, and uncontrolled. You say you describe the system configuration like before, just by the difference of hydrophilic and hydrophobic densities. Okay, that sort of says what is here should be the free energy functional as a functional of the difference of those hydrophilic hydrophobic densities. And you use the same order parameter as before. And then you can argue around that maybe DFT gives you some justification for that. But maybe DFT would also say it's not just hydrophilic hydrophobic, but I do need to know the density of the 25 speed, instead of just whether it's hydrophilic or hydrophobic. But okay, it's an assumption, and at that point there's no real justification except that it seems to yield reasonable results. Then you have to compute the free energy functional, and this we can do as before. So you want to take this trace, and we do this by this umbrella potential. The difference is now we don't have to use this heterogeneous multiscale model, and we don't have to make an ansatz, an explicit ansatz for the free energy functional, but we can sort of use it equation free, or the other school of Erik van den Eyden would call this the on-the-fly string method, how to calculate this. But once you have the free energy functional, or more exactly once you have the derivative of it, the chemical potential, then there's a very nice method to find the minimal free energy path in this landscape of the free energy, which then identifies you what should be here on the x-axis. So the y-axis is the free energy functional, and the x-axis is the contour length along the string. Yes, please.
To understand correctly, the energy of the stalk would be smaller than the energy of the two parallel membranes.
That depends on the parameters. At high asymmetry and high tension, yes, that were the pictures I have shown you. That would, I mean, in the previous graph where you saw the scattering and the TEM, the experimental pictures, that is the stalk phase or autorhombic phase, and that is thermodynamically stable. It's not the typical parameters for biological fusion. There you would expect that the stalk is only metastable. So in this case, that one would be even higher than this. And the fusion pore would be another barrier, and it would go down to the fusion. Okay. So
Excuse me, at that moment, your model for the lipid here, how does it look? Or is there there's just one particle per lipid?
no, it's. I mean, we come from polymers, so I excuse myself. It's a diblock copolymer, and the solvent is a homopolymer.
But there is every bond
Yeah.
is there.
Yeah. Well, I mean, there are bonds.
So
Whether these are the bonds of the lipids, one can argue about.
I guess what I'm asking is, you can have an asymmetry.
Yes.
It can be something like an effective spontaneous curvature.
Yeah, absolutely. There are 4, if I remember, hydrophilic beads and 28 hydrophobic beads. And that's so a symmetry of 1/3, which is close to the boundary between the lamella and inverted hexagonal phase. And that's also the biological relevant asymmetry for lipid membranes. If you make it more asymmetric, then you will favor more the stalk, and you will use the barrier as well. Okay, so how to get the free energy, I don't have to explain. We do it just as before. This is umbrella potential here. The good thing is, as I said, you don't need an ansatz. You just need the chemical potential. And once you have the chemical potential, then there's this very nice string method. So suppose you would have only 2-dimensional free energy. So in practice, of course, every point of your collocation lattice is 1 dimension of that free energy. Then you have a free energy hill somehow, and you want to find the minimum free energy path over this ridge in the free energy. So what you need is that at each point along the minimum free energy path, the force perpendicular to the path vanishes. And the force perpendicular to the path is written here. So it's the original force, or chemical potential, and then you sort of subtract the projection onto the path, and the path is parameterized by ms. S is the contour along the path, and that's of course a field in space. Okay, so you minimize this, and there's a very nice method how to do this, and you find this minimum free energy path. It's quite easy. The way you do is you propagate, you start with a guess of the path, you propagate it by the full chemical potential, so it goes down here, and then you reparameterize along the path in order to establish that the points are uniformly distributed along the path. So you don't even have to calculate that scalar product of the direction of the path and the chemical potential. Good. If you do it, it looks like that. So these are the 2 hydrophobic cores, and now you move along the path, which is like time, and you see that you form these dimples in the 2 membranes. And so the order parameter in this step is basically how far the dimples have advanced. And then the dimples sort of merge, they form this stalk. This is about the barrier, and then the stalk widens. So in the first part you would have the extension of the dimple, and in the second part you would have the width of the stalk. You also see that since it's a slightly compressible model where these 3 monolayers merge, you have this depression here in the density, which indicates the packing frustration. So if you then look at the free energy along that string contour, then here you have the 2 bilayers, here you have the stalk, which has the slightly higher free energy, and this is the barrier between it. And actually it does agree also very well with self-consistent field calculations for a similar model. And of course, you can do the test, right? Since you have at each point of this graph a particle-based configuration, you can just go to one of those points, generate whatever, 256 configurations, and just let them run. And you can ask whether they will end up in this minimum and in that minimum. And the probability of that is shown here. 50-50 is the horizontal line. So those ones who start left of this point run into this minimum, and those ones who start right of this point end up in the stalk configuration. Yes?
I was just thinking, is it possible to, so you start with 2 bilayers that have no stalk,
right?
No infinite stalk.
Mm-hmm.
Is it possible to go in some other direction to find a less favorable barrier, which doesn't look like a stalk? I guess if you were had another mesophase hanging around, which wasn't a cylindrical phase, but was something else, then you could get a more complex.
Yes, I agree. You will find sort of the path which is close to the one you have initialized in your string. If there are multiple passes, you have to initialize multiple strings. And if you didn't think of the right path, you will miss it. Yes. In this specific case, it's sort of easy, because there's this is the obvious one. Let's put it this way. If you go from the Stork to the fusion, there are more complicated ones. And there we are actually struggling and haven't found the one which we would like to find.
If there are interesting issues in dialogues about the different pathways that
Yes.
you can take between
Yes, absolutely.
potential or not.
Absolutely. Yes, yes.
So can you use this to...
Yeah. No, I mean, yes. I mean, for
I
the
guess what you can do, you can find them and find the energy barriers. So.
yes. I mean, let me come back to my open question at the end, then you will see another variation of what you say. Okay, we were very worried that the 50-50 chance and the barrier did not 100% agreed. Maybe that is pedantic, but the reason of that is this field theoretical umbrella potential assumes that lambda n goes to infinity, right? Only then the Gaussian becomes the delta function. But you can never reach this exactly, because if you make lambda n to infinity, nothing moves in your simulations, right? So there's another way to if you're in the vicinity of that, you can of course use the density fluctuations in the restraint model to back out a quadratic form of the free energy in the original model and use this to find the saddle point. And if you do this, and so these are the formulas of what I just said, so you look at the scattering in the constraint model, you back out the scattering factor and the quadratic form of the free energy, and you subtract the umbrella potential, then you get the following. So this is what you find with the string method, and this is what you find with the fluctuation analysis. They look very similar. That's good. If you take the difference between those two pictures, you get the following, which means that there's a little bit more red, i.e. hydrophobic, in the transition state of the fluctuation analysis. And that is quite compatible with the fact that this one here shifts from here to there a little bit to the right. So the stalk is a little bit thicker. So that's compatible. So we think the difference between these 2 points is simply that lambda n cannot be or was not high enough in the simulations. Okay, you can do more complicated things. So of course, if the stalk, yeah.
Another explanation, maybe it's the same thing, is that you would argue that the P1 half point is at the maximum, only if the kinetics of going both ways is symmetric. But if the kinetics is asymmetric, you might expect there to be something.
Yes.
Is that right?
That's a good point, but it's not addressed here because both, I mean, the fluctuation analysis and the string are both completely static methods. I mean, it's true that it would be another reason why the dynamic thing with the probability would be different, but it would be an alternative explanation. Okay, so let me see whether this movie works. Obviously not.
5 minutes.
Yeah, I'm as good as finished. Okay. So here you see that the stalk expands, right? I mean, this is one of the fusion pathways, becomes thicker and thicker, and then eventually you nucleate a pore inside, and that finishes fusion. You can look also at this pathway. And here there are alternative possibilities. So you need not to have necessarily this actually symmetric pathway, but you can also form a pore close to the stalk. If you look at the free energy barrier, then actually you see 2 barriers. So this is the stalk, this is fusion pore, which has now a lower free energy. The first is associated with the expansion of the stalk to sort of a hemifusion diaphragm, and then there's a second barrier where you rupture the hemifusion diaphragm in the middle and create this fusion pore, and then this here is downhill, opening up the fusion pore. Okay, with this, I'm at the end. I hope I have shown you that these soft coarse-grained models are useful to look at these collective phenomena, that the kinetics of structure formation is challenging there, that we devised these methods how to go from the particle-based description to this continuum free energy, where you describe the free energy functional through the densities, either by this umbrella sampling or force matching, that these continuum free energies can help you if you have these intrinsically slow processes, either due to a mismatch of disparity of forces or small Onsager coefficients, and they can also help you to find barriers and pathways in this free energy landscape. Okay, so some open questions. There are two. So we looked, in principle, the free energy landscape of these diblock copolymers are very rugged. In fact, people have related it to the free energy landscape of a glassy system. So there are many sort of metastable states around. That's well known. But what would be nice is if you could design your kinetics of ordering as to trap the system reproducibly in one of those metastable states. And I think that's particularly good for polymeric systems, because you can actually prepare highly non-equilibrium states easily, because you can change the thermodynamic parameters much faster than the fastest spinodal mode in your system, right? So, if you change something, you really prepare the system far outside of that equilibrium. However, if you do this, then you should, of course, also worry that the chain configurations are not necessarily in equilibrium with the density fields. That sort of relates to the fact that at the very onset you said, well, I look at the free energy as a function of the local densities, but of course there are other slow variables around. One of them could be the stress, and that would also relate to this viscoelastic phase separation business. So it would be nice to sort of try to generalize these methods where you can calculate the free energy as a function of the densities to basically the strain of the chain configurations. So that would be one question. The other question is, if you look then at the kinetics of phase separation, then of course it's sort of like a trivial statement, but if you want to direct the kinetics from this unstable state, then you really don't want to look at this minimum free energy path, because the minimum free energy path is model A. So you just minimize your free energy and look where it goes. But that's not what the system does. The system, of course, follows model B, which has this local conservation law. And so the question is whether there would be a similar good method like the string method, where you can say, okay, I have this start and end point, and I look at the kinetics between those 2 points in order B. Maybe that's too hard, because of course it's a first order differential equation, so you better don't describe the starting and the ending point. But maybe it's good enough to say, I know where I want to end up, this is the metastable state, and what is the region of attraction using this dynamics here. So anyway, these are quite general questions, and I thank you for your attention.
You start setting up while we have any other questions. I have one. So it seems to me you said you essentially had to see where your microscale system was going to get your entangled down to right, to then essentially extrapolate
yes,
at the continuum level. So in a sense, how much better is this than if I just fit the light decaying exponential extrapolation through the time scale? Is it a fancy way of extrapolating?
No. I think, you assume that the free energy functional stays constant for that, and the same assumption you convey to the Onsager coefficient, and then sort of, there are two ways. Either you sort of fit sort of a short time evolution, or you do it a little bit more fancy, where you say, I think I know what I have to look for, and then I maybe set up an interface, look at the motion of an interface or the sharpening of the interface, and that would be a way sort of also to get a better handle on the wave vector dependence or the non-locality. So one of the graphs which were there had information about the non-locality. The standard assumption is that it is related to the single chain structure factor. And again, here you would see that it's not exactly like that, because the chain conformations are slightly distorted, so it's between homogeneous and that one. Yes.
I suppose I'm interested in the question of how long can it be?
How wrong?
How wrong can it be?
I think if you directly fit the time evolution of the system you're looking at, you're pretty good.
Right.
I mean, even the homogeneous one was only 25% off. I mean, if you take, okay, the question is whether this is now a lot or not.
Yes, exactly.
Yes.
We can argue about that.
Yeah.
One quick one.
I'm a bit confused. When you had in the beginning the whole annealing was a hole, right? You had also two parallel membranes with a hole. And unlike the K formation, when they two come together, in this hole you had like a diffusion. So the question is why it never, when you had the hole, the first membrane was coming the same way as for the fusion case.
Right.
Why the first membrane was not approaching this hole and annealing in the other pathway. I'm asking about the pathway of annealing.
Oh, I
and
see.
not just the diffusion. So
I mean,
two
basically
similar
they
things.
collide
Yeah.
and then sort of exchange mass.
So they collided
yeah.
in the same way as fusion.
Yes, I think that is still slower. I mean, you could have the same mechanism in this Lifshitz-Lyorsov thing. I mean, alternative to evaporation would be droplet coalescence. And in small molecular fluids, I believe, these are comparable. They also yield similar time dependencies. In these macromolecular fluids, the diffusion of this domain, or the fluctuations of these membranes are even slower than the evaporation process, because the viscosity of the system is so super high. So if you drag the spherical domain through it, or if you look at the diffusion constant of that thing, it's super low. So I agree that
But
is
this
a possible.
Diffusion was dominating. Okay, so
Yeah, but the question is whether you diffuse a whole domain or you diffuse a single molecule.
Thank you very much again. We now move on to our next speaker,